Before I start, just want to say, for those of you who don't know, Lise Meitner is actually the person who discovered nuclear fission. For a series of concomitant reasons, she was never given the Nobel Prize. She used to work at what used to be the Max Planck Society during the war. And so I think it's great that the Max Planck Society is now acknowledging her contribution to science. So what I'm going to talk about is, I said, strong gravitational lensing. So we're going to look at multiple distorted images of the same background source. And this creates very nice pictures, which are not really pretty to look at, but they are very interesting from a scientific perspective. In particular, we can use this type of images to learn about the matter distribution of the universe. This is why it's useful for dark matter. We can use it to look at distant galaxies in a magnified way. So it's really interesting to learn about the distant universe in a way that you wouldn't be able to do without strong lensing. And they also provide information on the plasma and the magnetic fields in lens galaxies. But today I'm only going to focus on dark matter. So I was actually going to give a review talk, but then I realized I only have 20 minutes, so I decided to be selfish and only be focusing on galaxy-galaxy lensing and present the work that my group and I have been doing in the past few years. Myself, together with other people in the room, we've been recently writing a review on the topic. It's already becoming out of date. But if you want to get a sense of where the field was up to a few weeks ago and get an idea of the challenges and potential pitfalls of this type of measurements, I recommend you have a look. Also, if you can't sleep at night, it's probably a good read. So the idea is that gravitational lenses sees all type of matter, all the way from the observer to the background source, and is particularly sensitive to the presence of low mass halos, either within lens galaxies or around the line of sight. But essentially, you can probe any dark matter model that makes predictions on the dark matter distributions on sub-kiloparsec scales. Now, it's a gravitational probe, so in a sense, it doesn't care about baryons in a direct way, but it's incorrect to say they were not affected by baryons. And those come up in the systematics and in other kinds of challenges, right? And I'm going to mention some of those later on. So I'm looking for individual sub-halos and field halos in lens galaxies. And over the years, about 50 lenses have been analyzed, 30 by myself and my group. The entire sample of 50 LUX lenses by the group in Durham. And so far, only 2 detections have been reported. There was a third one reported with ALMA. However, neither my group nor the group in Durham can reproduce the ALMA detection, and therefore I took it out. And if you're interested to know more about it, please come and ask me later. So these 2 detections, one was made with the HST at Redshift 0.6, a mass of around 10 to the 9 solar masses. The other one at Redshift 0.8. And the way you see them here is the way that I detect them is like localized density correction to your overall smooth distribution of the galaxy. Now, if both detections have been confirmed by independent group using completely independent lens modeling code. So this is encouraging. I'm quite confident about these 2 detections. Unfortunately, from a dark matter perspective, they're not that interesting, right? We could have not detected these objects without lensing, but they're rather massive, so they don't probe the mass function in a regime that is particularly interesting for ruling out dark matter models. However, we can also use together detection and non-detections to try to get constraints. These are, unfortunately, our current best constraints, which are not particularly interesting. So these are 2 samples of gravitational lens system. You have 11 galaxies here and 20 here. And that's, as a comparison, those were the constraints at the time from the Lyman Alpha Forest and the Milky Way satellites. So our constraints at the time were not as competitive as alternative probes. I believe they might be more robust, but this is to be discussed. And the main reason why these constraints are not competitive is 2. One is the limited sample size. We only had 30 objects. But the real limiting factor here is the quality of the data, the angular resolution of the data. So I often see in papers people write, oh, with gravitational lens arcs, you can only detect 10 to the 9 subhalos. Wrong. There's not a single number that you can attribute to a lens, and I'll show you that in a minute. So we wanted to improve our constraints, and so we spent a lot of work working with simulated data. And the questions that, in particular, Julia has been working on a few years ago was, how many lenses do we need to test CDM, and what is the best strategy? Should we go for larger samples? Should we increase the signal-to-noise ratio? Or should we be focusing on angular resolution? So what I'm showing here is what we call the sensitivity function. So These contours are the lensed images for the same gravitational lens system, and each pixel is the lowest detectable, in this case, sub-halos in each pixel. So you can see you cannot give a number, because this number depends on each position, and it will change significantly from one gravitational lens system to the other, because it's also depending on the underlying magnification. So here is if you observe the same gravitational system, let's say with Hubble, with 1, 4, and 10 orbits. So you can see that the effect of the signal-to-noise ratio is to increase the area in which you're sensitive to the presence of low-mass halos. But it doesn't change how deep you probe the mass function. And as I will show you later, unfortunately, you lose a lot of this area once you start considering more complicated mass distribution for the lens galaxies. But I will show you that later. So what happens if you look in terms of detections, if you don't go much deeper in the mass function, so detection increase, but not very strongly. On the other hand, if you increase the angular resolution just by a little bit, so let's look at Keck adaptive optics instead of with the HST, suddenly you increase your sense, so the area stays the same, but you go much deeper. So pixels that were already sensitive become even more sensitive. And because the mass function is a power law, you gain a significant number of detections just by slightly increasing the angular resolution of the data. Okay? And what is cool is that unlike the low-mass halos, which are way far away from the lensed images, the ones close to the lensed images are less degenerate with other unknowns in your model. So this is just to give you an idea. We're currently analyzing a sample of 30 lenses observed with KKO, and this is how we expect our constraints to improve in the next, hopefully, months. But this is good, but it's not good enough. What we really want to do is to probe the halo mass function in the regime of 10 to the 6 solar masses. And as I said, you need to do this with angular resolution. Before I do this, what is the role of Euclid in all this? And if you've been listening, you probably already know the answer. Now, Euclid is great, is running, and we already found lenses. We actually already modeled lenses with Euclid. And the number of lenses that we found so far with Euclid is consistent with the prediction by Tom Collett. So it does seem that indeed Euclid is going to deliver around 10 to the 5 new gravitational lens systems. So we're really excited about it. However, so Euclid is going to allow you to detect loads of substructure just because you have loads of lenses. But here is the number of detectable objects per lens as a function of MHM, so the half-mode mass. These are different detection significance. These are constraints that were there when we made this plot. So Euclid is going to allow you to detect one substructure every 70 lenses. Okay, this is a lot. We have 2 at the moment. We're going to have huge. The problem is that because of the limited angular resolution of Euclid, all these detections are going to be quite high on the high mass end of the halo mass function. So Euclid is not going to allow you to probe the cutoff in the mass function. What it's going to allow you to do is to measure the other parameter, the normalization of the mass function in the massive end. And then we can use this as a prior for our higher angular resolution constraints. The other thing that Euclid is going to be good at is because we're going to have so many lenses, is going to be able to tell you how much the normalization changes with the host redshift and the host mass, so that we have to stop assuming those from simulation. We can actually test those predictions. And the other thing that I'm really excited is Euclid is going to allow us to study the mass distribution of lens galaxies so that we can start getting a handle on one of the biggest systematic error and uncertainty in our lens modeling. But as I said, we really want to do better, and at the moment, the only way to probe the halo mass function in the regime of 10 to the 6 with gravitational lensed extended objects is to use very long baseline interferometry. So these 2 images are the 2 highest angular resolution images of a gravitational lens ever taken. And they are so sensitive that if you had a 10 to the 6 or 10 to the 7, you could see the effect of a subhalo or a line of sight halo by eye. Okay, so I know I've been showing these images for a long time. We've been promising results for a long time. But this data is really challenging to model. So this is a radio interferometers. We connected the EVN in Europe with antennas in the US. And this is actually what the data is. So the data lives in Fourier space and is huge. We have 10 to the 12 visibility points. We had to develop dedicated lens modeling codes just to be able to do this. And Devon Powell, who is a postdoc in the group, has been amazing in dealing with the numerical challenges just related to analyze this data. But we finally have a lens modeling code which is robust, is actually relatively fast for this type of data. And because it's fast for this type of data, it's really fast for Euclid-like type of data. And we're actually thinking of using the code to model the entire sample of Euclid lenses. So the code is an extension of what I originally developed in 2009. So it can deal with optical data, radio data, 2D data, 3D. So if you're looking at emission lines and study the kinematics of our redshift galaxies. We recently extended it to the polarimetry domain, and we are currently exploring how to use strong gravitational lensing to learn about magnetic fields. The code is not public, it will remain not public. However, we're really open to collaboration, so if you're interested in working with us and using the code, please get in touch. If you rather use a publicly available code, then I highly recommend those by our esteemed competitors at the University of Durham. So I really recommend PyAutoLens if you really don't want to work with us. So when you have milliarc second resolution, there is really a lot that you can learn about the mass density distribution of lens galaxies, right? So you're probing these on very small scales. And what Cristiana Spingola and Devon have found is that the typical assumption that people have been doing for many years when modeling lenses, namely that galaxies are well described by elliptical power laws, only explain the mass distribution up to 98%. And you can say, okay, that's good enough, no? Do you really need to model lenses down to 100%? And the question is, to a certain extent, yes, because a small change of 2.4% in the complexity induces an error on H0 by 3% and an error on the flux ratios by 7%. Okay, so really getting the mass distribution of your main lens is fundamental for precision cosmology. Just to give you an idea, the model that best fits the data contains a power law, multiple angular structures of the order 3 and 4, also an external potential because it's part of a group, and of course external shear. Because the data is very sensitive, once we found a good macro model, we could start looking for perturbations on top of these otherwise smooth mass density distribution, and we were really interested in testing fuzzy dark matter models. So what I'm showing here, these curves, these Y curves, are what we call the critical curves. So you should think of an isodensity mass contour. And as dark matter gets from more fuzzy to less fuzzy, you see you get the mass density distribution of your galaxy is less granular, so you get very smooth critical curves. And on the other way, you get loads of granules, and so you get all these jagged critical curves. And what it means is that if you take 2 points on the lens plane, they should map back on the same position on the source plane they don't do on a milliarc second scales, okay? So we use this, and basically you're unable to reconstruct your source, which should look like a jet. So this is the real data, it's not simulation. It should look like a jet, but it looks like a car crash. So we use this effect to try to set a limit on the fuzziness or on the mass of the particle. To do this, we assume a Gaussian random field with cross-section, correlation length that is inversely proportional to the velocity dispersion of the galaxy, and we tested this assumption against the simulations run by Simon Mai and Elisa Ferreira. So here are constraints from different probes, and you can see that with just one gravitational lens system, a milliarc second resolution, you're really able to get interesting constraints. We have even higher angular resolution data, so we hope that this will move slightly on this direction. Here, off the plot, you have the constraints by Dalal using the velocity dispersion of the Milky Way satellites, and because of this, and because lens galaxies tend to be massive elliptical galaxies, it's going to be really, really hard for lensing to be competitive with these probes, mainly just because of this effect, essentially. So we might not be able to do much better than this. Okay, so I said that if you have a 10 to the 6, you can actually detect halos just by looking at it, and can we actually detect 10 to the 6 sub-halos? And the answer is yes. And so this is the arc, and if you look at here, there's a gap in the arc. If that gap were part of your source, you would see it in multiple locations, but we only see it here. And these are not the images we analyze, but I can't think in Fourier space. Maybe you're better than me at that, so I'm just going to show you the images, but this is not what we model. When we model the visibility space, we find that this gap is consistent with a substructure with a mass of 1.3 10 to the 6 solar masses, and the difference in Bayesian evidence between a model that includes and doesn't include is at the 62 sigma level if we were not dominated by systematics. Of course, when you get to this regime, you start worrying about globular clusters. So I refitted the data using a King profile. And I find that you could have a globular cluster with a mass of 1.5 10 to the 5 solar masses. Interesting though, is not preferred as much as isothermal profile. Okay, and we're currently testing for systematics. We're currently testing more models, but possibly this is the smallest detections of a subhalo or a line of halo. We're testing that as well, ever made. So we're really excited about it, and we're trying to understand now what does this tell us about dark matter models. Note that if you lived in a CDM universe, you would expect only 11 subhalos between 10 to the 6 and 10 to the solar masses in this entire area. Okay, so the price that you pay with high angular resolution and that you're decreasing significantly the area that you're probing. Okay, but you might want to say, okay, halos don't come on their own; they come as a population. So okay, you have a 10 to the 6. What are all the other ones? So what I'm showing here are simulations where we race through large population of low mass halos in different amounts. And I just wanted to see, okay, can we use the fact that we have a thin, straight arc to get extra constraints that are more than what you would just get from the detection? And in principle, yes, because this population completely disrupt the arc. However, you can see there's many ways that you can disrupt the arc. And unfortunately, there's also many ways in which you can restore the arc, because the large population of low mass halos, as I've been saying for many years, is highly degenerate with the macro model. So I can change my macro model, and even though I have plenty of subhalos, I can restore my arc. So really, we are in the single detection regime, and despite what people say, the population rarely brings extra constraints. And here I'm going to put out my old person hat, so I'm going to be the Frank of the situation. And don't get mistaken, I'm not grumpy because my age is closer to that of Frank than to many of yours. I was born a grumpy old man. So Frank has already talked about all the pitfall of assuming mass function from simulations. I'm not going to go into that. I just want to point out a recent paper by Felix Heinz and Julia Despali, where they looked at TNG50, and turns out the subhalos are not well described by an NFW profile, but you need something more concentrated, but also steeper at the center. And this could have impact when you interpret your detections in terms of CDM and SIDM. So really having good predictions, not just for the numbers, but for the profile is important. Now, this keeps me awake every other night. What really keeps me awake every night is the degeneracy with the macro model, okay? So what we've been doing with Connor, a postdoc in the group, is we asked ourselves a question: if galaxies have angular structure, what does it do to our detections? So we train a neural network and analyze thousands of galaxies, and we train them to look for substructure, and then we created a separate data set where there's no substructure, there's only multiples of order 2, 3, and 4. And we asked the network, can you tell us in which of the systems are there substructure or not? And what it turns out is that because the network didn't know about multiples, it reported a high number of false detections. Namely, there's a high degenerate between complex angular structure in the lens and low mass halos. When we retrained the network to know about the existence of multiples, the false positive dropped down. And this really indicates that the origin of these false positive detections is unaccounted for complexity in the mass density distribution. What this means in practice, this is again the sensitivity function, so the lowest halos that you can detect. This is if you don't account for multiples. This is if you are for multiples of order 3. And this is if you account for all multiples of order 3 and 4. So as I said before, you lose a lot of sensitivity in the outer areas. And this is in a sense, so if you don't account for this, not only you're going to get constraints which are not robust because you are overestimating the reliability of your detections here, but you also miscalculate your proposal, right? You're going to ask for lenses, and suddenly maybe here you're only going to ask for 10, but actually it turns out you maybe need 100 lenses to do this, right? So it's really important to get this right, not just for the constraints, but also for planning for the future. So you need to account for that. And you could think of using the isophotes of galaxies to get a prior on the multiples, and the answer is not. We've been looking at ALMA lenses, and we show that often the isophote and the mass density distributions do not match each other. We only did it for 3. We now have a sample of 10 lenses, and the idea here is to understand how much light, how well light traces mass. So to end on a nice note, we detected 1 10 to the 6. The question is how many more of this we could do. And it's a great time for lensing. Euclid is really on the way to detect loads of galaxies. Hopefully SKA will follow, and we already have high resolution facilities. I hear from colleague next door that ELT is on track, and so it is really an exciting time to work on lensing. And I'll finish by advertising a tenure track position in the group. So if you're into high performance computing and want to work on lensing, please apply. Thanks.